Okay, now I have started recording for the class, and yeah, our today's topics, if we refer to the textbook, it still be in the chapter 2 and the second part of the chapter 2. Last week we learned about how to find the mathematical model to describe the component of mechanical system like mass component, spring, and damper component. So by that knowledge, in today's class, we will try to use that information to complete deriving the mathematical modeling of single degree of freedom system. So we still left one part from last class. This part is the external source. External source can be a kind of non-conservative force or conservative force that apply to the system. And today we are talking about how can we find the mechanical work or mechanical power that relate to the force, the external force. And external source for the system not only can come from the force, not only can come from the form of force, but sometimes the motion that we apply to the system can also be considered as input to the system. We call a motion input. And we can find the equivalent force that can describe that motion input. And today we will talk about this. And if you still remember in the first week that we met, I tried to derive the equation of motion of some simple system by drawing a free body diagram and find the equation to describe the equilibrium of force and moment and derive the equation of motion. Today we will go in the detail of this again, and we have a lot of example so that you can more familiar with how to obtain the equation of motion through the free body diagram method. And we also talk about a kind of static equilibrium due to conservative force or gravity, the relationship between the gravity and the spring deformation. Today, we will review that concept again. Sometimes when we work with the mechanical system that have spring as a component, we may confuse which level should be the datum or the reference of the system. So by knowing the concept of the gravity and static diffraction relationship, we may have a better way to select the datum of the system to consider the energy or consider the force of the system. Sometimes we don't need to consider mg and the static diffraction. Every time we can find some way to ignore this force and diffraction, like it has a kind of cancellation. And yeah, we can make the equation more simple and easy to understand by remove the mg and the static diffraction. And we also had already mentioned about the small angle and small displacement assumption to make our equation to be linear equation, linear differential equation. So we will see some example of equation of motion that is nonlinear and contains some terms of nonlinear terms. And we will discuss which type of nonlinear term that we can simply remove from the system by the assumption of the small angle and small displacement. And from last week, we learned how to find equivalent stiffness, equivalent mass, equivalent damping coefficient, and it seems like in complicated systems, we learn how to find that equivalent property. And this week, we firstly begin with the free body diagram method to obtain the equation of motion. Just only for some simple problem that we can draw free body diagram of few components, but for a complicated system, for various complicated system that we need to draw multiple pieces of component in the system and draw free body diagram of each component and obtain the several equations and solve the equation to obtain the final equation of motion of a single DOF system. The single DOF system can have only one equation of motion that relate to a generalized coordinate that we select. So although you have 10 pieces of object in the system, you may begin with conduct like 10 equations, but finally you need to solve all the equations to derive only one equation of motion from that 10 equations. So maybe it's not easy to do. So the equivalent system method will take advantage of the equivalent property that we derived from the last week to compose an equation of motion. It's a good alternative, and we will learn it today. And yeah, this is the first assignment. We're gonna have a first assignment for today, and it's gonna take 5 points from the total 100 points. So the assignment is not difficult. I just want all of you to review the content from the past week and including the content in this week to derive equation of motion. And yeah, the assignment is 5 points, and the submission you can prepare the answer sheet in the software, and also you can write it down on a paper and just scan it and submit it as a single PDF file on Moodle. And the deadline is on Monday before midnight of September 7th. And yeah, you still have maybe 2 weeks, around 2 weeks to complete the assignment. Yeah, as I mentioned, I still didn't add all of you in the Moodle. So I will try to do it by maybe today or tomorrow and add the past lecture slide and the record Zoom. And we'll add the assignment into the Moodle also so that you can use as reference. So going to the content for today, the concept of the work and power. The work that done by non-conservative force is part dependent. The work that done by non-conservative force, the example of non-conservative force, such as the viscous damping force or externally applied force, is part dependent which means if we want to find the work, we need to do the integral of the force and the displacement, and it depends on the direction of the force and direction of the displacement in any time along the path. And in our problem, many times the force is a function of time instead of the generalized coordinate. So the original equation to compute the work is the integral of the force along a generalized coordinate. But we can modify dx to be the velocity multiplied by the dt. And if we have many external force in the system, if we have more than one force, the total work done by the external force is the summation of the integral of each force against the displacement, or if you find the equivalent force to the system, instead of do the summation of the integral, you find the equivalent force and you just integral the equivalent force along the generalized coordinate. We also can do this, and the okay, you asking for the slide for today's lecture. Okay, I again add the slide for today's lecture. I answer your question, Tat Lawin. Okay, if your friend just attend the class later than this, I want to ask for your guys' help who already have the slide. Please share to your friend, okay? And the work is the cumulative property from the initial position to final position, or the time, initial time to final time. But the mechanical power is instantaneous property. We can obtain the power by the first time derivative of the mechanical work function by dt, or you may familiar with like the power is equal to force multiplied by the velocity. Force is a function of time. The velocity also a function of time. And at any time point, when t equal to maybe t0 or some constant, you can find a value of the mechanical power and its instantaneous property of the system. And we need to the power is equal to the first time derivative of the work by dt, and the work function is this. And here x1 is x at time t1 at the initial time, and x2 is x at time t2. This is the relationship between x2 and t2, x1 and t1. And yeah, the x is equal to x dot dt. Okay, here is the concept. To get you more clear on this concept, we may spend a little more time on this example. And okay, we're gonna compute the work and power for a given force function and position function. If we want to deal with number, we may simplify what the problem gives as a simple in the symbolic. Ft force function may be written in the terms of the magnitude multiplied by the psi function of omega t. And yeah, the position xt is written by the magnitude multiplied by the function psi of omega t plus 1 phase shift. So if we want to find a work done by a force between time 0 to arbitrary time t, the mechanical work is the integral from t1 to t2 of ft, and the x, or the integral from x1 to x2 of ft and x dot t dt. So now we already have the force function as a function of time, and we have the displacement as a function of time. We need to find the time derivative of the displacement. So x dot t, if xt is equal to b psi omega t plus the phase angle phi, the x dot should be b cosine omega t plus phase phi, and by the differentiation of omega t by dt, we have one more omega here. So if you want to compute the mechanical work, now you have ft and you have the x dot t. So finally, u will equal to the integral from x1 to x2. x1 also function of time t x1 when t equal to 0, and x2 when t equal to t. F is a sine omega t. X dot is omega b cosine omega t plus phase dt. Do you have any idea to do the integral of the function that still have the product of the sine and cosine? I'm not sure you still remember the trigonometric property. Okay, we may begin with sine of A plus B. If you don't want to remember a complicated property, you may begin with the simple one that you can remember. Sine A plus B is sine A cosine B plus cosine A sine B, right? How about sine of A minus B? Sine of A minus B, sine A still be the same. Cosine of B is cosine B. Cosine of minus B still be cosine B. Cosine A is cosine A. Cosine of minus B sine of B is sine B, but sine of minus B will be minus of sine B. If you combine these two equations and divide it by 2, what you have, if you combine these two equations, these two terms will cancel, and what you have is sine A plus B plus sine A subtract by B will equal to 2 of sine A cosine B. And if you want only sine A cosine B, then you can get like sine A cosine B is equal to 1/2 of sine A plus B plus sine A subtract by B. Now this one and this one are in the same form, and you can separate these two terms into these two terms. I want you to try at home. Now we combine these two equations. I want you to try to subtract these two equations. Subtract this one from this one. And then on the right hand side, instead of this, you may get like 2 cosine A sine B is equal to the subtraction of the left hand side, and you can derive the similar property. Okay, so until now, from here, what can we get from here? We can move A, B, and omega outside, and the integral from the t 0 to t of this, by using this, you can get like 1/2 of sine A plus B. This is sine A and this is cosine B, right? Sine A multiplied by cosine B. you can get 1/2 of sine A plus B plus sine of A subtract by B. So A plus B will be 2 omega t plus phi. And what is the A subtract by B? A subtract by B, we're gonna have sine of minus phi dt. And now when you combine this term, you can separate the integral because the two terms of integral are combined instead of the product of two terms. So you can do it easily. And yeah, we have the constant that we know, and the omega, and also the phi. And yeah, we can do the integral. These two terms is the sine of the combination of two terms. You also can like separate it to this one, the sine of 2 omega 3 plus phi is sine A plus B. You can separate it to two terms like this, but the sine of the phi will be just a constant. And yeah, you can do the integral. And the work will be in the function of the arbitrary time t. If you want to determine the work done by this force between t equal to 0 to t equal to 0.01 second, you just substitute t by this number. After you obtain the integral, the integral will be written in the terms of the variable t. You just put t in the solution, and you can get the numerical value for the work that done in the interval from 0 second to 0 second to 0.01 second. How about the power? The power at the time t equal to 0.01, we don't need to do the integral if we want to find the mechanical power. We know that the power is the product of the force at that time multiplied by the velocity at that time. So the force is this function, and the velocity is this function. So the p at any time t is equal to the product of the ft and x dot t. So it will equal to a sine omega t multiplied by the omega b cosine omega t plus the phase angle. So at any time t, if you want to know when t equal to 0.01 second, you can find the value of the mechanical power at that point time. Okay. And the type of external force Ft can come in various forms. Sinusoidal force means here is the time, and here is the force function. And the force is a sine function against time. It can also be shifted vertically to be only positive force or to be only negative force, or it can also be shifted horizontally to be, yeah. And this kind of force we call sinusoidal force. The sinusoidal force is simply generated by actuator. Why we say this? If you have only one motor and the motor is rotated, it cannot generate anything. But if you connect the motor with a link that connect to another link and just like go into the linear motion, something like this, the motion that turn from the theta to the x coordinate, this kind of system, we may obtain the function as a sinusoidal function, and also the force that acts by the link, the force that transfer from the torque to the link, also as a function of the angle, maybe. So yeah, they mentioned that the force that generated by actuator, yeah, many times the actuator operate as like reciprocating, like continuous rotating, and by the linkage, by something, we can get the sinusoidal force from actuator. You may consider like engine force. In the engine, we have like multiple pistons that rotate with different angle. If you consider for each piston and cylinder, and we have the crank in the system, so the engine itself cannot generate continuous torque or continuous force, but it will vary with the time in the cycle. And this thing can be perfect sinusoidal in the sine or cosine form, or sometimes it can be a kind of like a harmonic force. A harmonic force means it don't need to be a perfect sine or cosine function, but it can be a kind of maybe this thing we also call like harmonic force, like it has the repetitive component or has a period, and it repeats in every period. We call it harmonic force. The harmonic force can be observed from the normal machine. For example, in the engine that rotate repetitively, or the rotating machinery. If you have experience with washing clothes with the washing machine, your clothes washing machine has a drum, and inside a drum you put your clothes. And when the washing machine rotates, although it rotates with constant angular velocity, but if your clothes in the machine create unbalanced mass, when the machine rotates, it can create the harmonic force. If you put this machine on a platform, and yeah, maybe you can put the machine on a scale, and you can read the scale change depending on time when the washing machine rotate and the force going up and down. It can create vibration, and this kind of vibration is also a kind of harmonic force with a constant period relating to the angular velocity of the rotation. The impulsive force, if you remember, impulse is the thing that happen in a very short time. And the magnitude of the force is big. And time is very short. Delta t is close to like 0. And we have the term of, if you study in like electrical engineering, they will call like unit impulse. The unit impulse means the integral of f dt from 0 to infinite. From t equal to 0 to infinite, integral of ft dt is equal to 1. Means the area here, the area under the plot between force and time, from 0, from time equal to, no, I make a mistake. From time minus infinite to infinite. The integral is equal to 1, which means we don't have the force elsewhere. We have only force when time equal to t equal to t0, and the integral of the area under the plot, the integral is equal to 1. We call this as a unit impulse. So by meaning, the impulsive force is a force that applies in a very short period of time. The example of this behavior okay, Cook, yeah, Cook sent a question that should I record? I already record this lecture, so don't worry. Okay, and yeah, the example for this phenomena is we use a hammer, and we hit a hammer on a surface, and the time that we apply the force is very short, and the magnitude of the force is high. Transient force is force that generates over a period of time. A transient force can be a kind of the step. The step means before t equal to 0, t0, the force is 0. And at t equal to t0, the force begin to apply. And after that, the force continue. This we call the unit step. The names of the force function is step. The unit come from the magnitude of the force is equal to 1. So we call unit step. Different kind is maybe RT is equal to t. When the time passes, the size, the magnitude of the force is increased with the time and has the linear relationship. And if the slope is 1, we call a function as unit ramp function. The unit step ut is equal to 0 when t is less than t0 and equal to 1 when t is more than or equal to t0. This is unit step. For the unit lamp RT equal to 0 before, maybe in this time t0 equal to 0. When t less than 0, the value of the function of the force is 0. But when the time more than 0, RT is equal to t. When t is more than or equal to 0. This one we call unit lamp. And the function of the force also can be Ft equal to maybe t squared or something like that. So we have different type of force function that change against time. And the response of the system that react to the input force also change against time. We call this kind of force as a transient force. Okay, as we mentioned that the external source to the system can be force or sometimes can be a motion input. The example of the motion input, many times we have like a kind of a cam follower system. Okay. Yeah. We call this one, yeah, this one can be a kind of cam. The cam means the radius from the rotating point to the contact point here. The radius change against the angular position, and the follower is travel in one linear direction. So we have the theta of the cam that rotates, and we have the x as a linear motion. So by kinematic mechanism of such as the cam and follower system, it can create the motion input to the follower by the cam. Another example that you need to know is the wheels that follow the road contour. The road contour means, yeah, when the position change, the road surface also change. The position may be x, and the level that change of the road can be like y. It's a function of x. So this one we call road contour. If the road travel, if the car travel at one constant speed, and we know the function of x as a function of time, y, that is a function of the x, can be related to a function of time. For example, if you drive a car with constant speed on a road that has a contour as a sine function, yx equal to maybe y0 plus a sine x. And you know that x is depend on time. If your car travel with constant speed, for example, at 2 meters per second, if your car travel with a constant speed, you can know that xt, or position of the car, can be defined by the velocity multiplied by time. So xt is velocity multiplied by time, and the road contour is a function of the position. So you can find the contour of the yt by substitute the function of the position into this function. You can get yt. But what we're gonna find in this slide is how can we find the equivalent force as a result of the motion input. The motion input to the system is the vertical change position of the wheel. So what should be the equivalent force that acts on the system by the motion input? We're gonna draw the free body diagram of the mass M. We have the mass M, and the generalized coordinate to this system is the x, which change against time, and x may measure from the free length of the spring or from the equilibrium position of the system. But the force mass has mg. Every time the force mass has mg. What should be the force done by the spring and the damper? The force that done by the spring and the damper is depend on the relative motion of the wheel and the body of the vehicle. We assume that the yt, or the motion of the wheel, always bigger than xt, and the velocity of yt always bigger than the velocity of xt. If I assume this, what we can imagine about the system? If yt always more than xt, if yt always more than xt, it means that the spring is under stretch. So it means that the wheel try to pull the spring downward because yt is bigger than xt. So the spring force will go into the downward direction, and the magnitude of the spring force will be the spring constant multiplied by y, subtract by x, or the relative displacement between y and x? How about the force by the damper? The force by the damper also in the same way. It will be the damping coefficient multiplied by the velocity difference. But if y always go faster than x dot, which means we also try to stretching the damper also. So the force will go in the downward direction. And if we find the equilibrium of force in the vertical, summation Fy equal to MAY. In this case, it seems like we put the downward as positive. So what we gonna have? Downward positive, right? So we have K Y subtract X plus C Y dot subtract X dot and plus mg is equal to m x dot dot. This y, okay, it seems to make you confused between y and x. This direction just only to indicate that we are consider the thing in vertical direction. Okay, so it should be something, maybe we can use the z as a vertical parameter, or we can use x or y. It's also fine because both x and y are in the vertical direction. But yeah, in our case, we are interested in the coordinate x, so let's use x. But x in this case mean the vertical displacement. The summation of the force in vertical direction is equal to the mass multiplied by the acceleration in the vertical direction, and the downward is considered as positive. So the spring force, the damping force, and the mg all are positive because everything are in the downward direction, and equal to the mass multiplied by the acceleration, also positive in downward direction. So what can we get from here? We can derive it as mx dot dot plus cx dot plus kx equal to ky plus cy dot plus mg. Now, the dimension of the equation is the dimension of the force. The dimension of this is the dimension of the force. You can consider in the unit, the mass is kilogram, acceleration is like meter per sec square. Yeah, or this one, K is Newton per meter multiplied by X, which is the meter. Yeah, by dimensional analysis, this equation is written in the unit of the force. And these two terms are the force that is the result of the input motion. So we can call this one as equivalent force due to the input motion. So the equivalent force due to the input motion of this spring damper system is equal to the spring constant multiplied by the displacement plus the damping coefficient multiplied by the velocity of the motion input. So yeah, we can derive the equivalent force from the input motion y. Okay, that's all for this slide. Okay, do with the example. This example is the review of this slide, that we know the rod function and know the velocity, and we try to find the equivalent force function. We know the bumpy rod function. The bumpy rod function is written by the car travel by the vertical displacement is a function of the distance, and it's a kind of psi function A psi omega and the C, but it's still not related to time. But we know that the car travel at a constant speed. The car travel at constant speed. So what should be the Z as a function of time? The position as a function of time is the velocity multiplied by time. So Z is 60 multiplied by T. And this is the load function. That is a kind of psi function as a function of the displacement, but we know the displacement as a function of time. So what is the time dependent displacement impart to the suspension system? This is the displacement as a function of the horizontal position. But if we want to find the time dependent displacement, which means we need to find y as a function of t. The problem gives y as a function of z, and you know z as a function of t. You can find y as a function of time. And what is the acceleration impart to the suspension system? You know yt, you find the second derivative, you can obtain the acceleration. What is the equivalent force felt by the vehicle through the suspension system? From the previous derivation, we know that the simple suspension system that have the spring and the damper, the equivalent force is stiffness ky plus cy dot. So equivalent force is equal to ky plus cy dot. We know k, we know c, and we know the function of yt and we can find y dot t. And if we put everything into here, we can have the force equivalent as a function of time. And this is the answer of this question. Yeah, you need to familiar with like how to substitute the number and obtain the numerical solution. But don't worry, in the exam, I will try to not use the number. I don't want you to use calculator too much. I always tack with the problem in the terms of variable. Yeah, it seems like we can understand the physical meaning and imagine what happened and don't need to make a mistake on the computation on the numerical thing. But in the real application, yeah, you need to deal with the number. But to get the concept in this class, I will try to mainly teach you and have the exam problem in the symbolic expression. And how to derive the equation of motion of the spring, mass, and damper system. I hope at the end of this class, all of you can deal with this problem. This may be the third or the fourth time that we gonna write down the free body diagram and derive the EOM of this system. We have the mass that put on the surface. So the free body diagram, we should have the normal force from the surface, and the mass has the gravitational force mg. We have the force Ft to the right hand side. We're gonna assume the coordinate xt that begin from the equilibrium position of the system. So when the box moves to the right hand side, the spring force will go to the left hand side. The magnitude of the spring force will be kx. How about the damping force? We also need to assume the velocity of the system to the right hand side also. And the magnitude of the damping force will be C multiplied by x dot. So we're gonna sum the force in the horizontal direction equal to mass multiplied by acceleration. And maybe to the right hand side is positive. X is positive and x dot is positive to the right hand side. So Ft subtract by kx and cx dot equal to mx dot dot. So we just rearrange the equation to separate the terms of the generalized coordinate on the different side of the input. So we're gonna have mx dot dot plus cx dot plus kx equal to ft. Now we can relate the motion that described by the generalized coordinate as a function of the input force. Or in the previous example, the motion as a function of the input, but input motion. Okay. How about in like torsional application? Before this is linear application. In linear application, F equal to Kx. In torsional application, the moment of the torsion beam is a function of the angular displacement. The torsional stiffness is written in this term. Okay, in this problem, we have one torsion beam. The torsion beam have the cross section as a circle, and the length of the beam is L. The moment of area J. The material property G. This may be the shear modulus. We already talked about this in the last class. We have the length, the second moment of area, and the material property, or the shear modulus. This is the torsion bar, torsion beam, and at the end of the beam, we have a disc that rotates. In this problem, we want to find the equation of motion when we rotate the disc. What should be the relationship between the generalized coordinate theta and the input effort or the moment? So if we see the disc on this section, on this view, if we see the disc on this view, we can see a circle, and we assume the theta is positive in the clockwise direction, and the moment that apply, the external moment mt, or moment as a function of time, also in the clockwise direction. But if the beam is rotated clockwise with the angle theta, the moment by the torsion bar on the disc will go on the opposite direction. The torque by the torsion bar act on the disc will go in the opposite direction to the angular displacement. So angular displacement is in the clockwise direction. So the torque due to the torsion will go into the counterclockwise, and this moment is equal to Jg divided by L theta. I want you to imagine one thing. If the cross section of the bar are the same, material property are the same, do you think the short bar or the long bar will have a higher stiffness? The stiffness, the torsional stiffness, is inverse with the length of the bar, which means if you have a long bar, you can rotate it and make it deform easier compared with when you have a short bar. Does that make sense? Okay, to obtain the equation of motion, we're gonna do the summation of moment about the rotational point, maybe assume as O, equal to the moment of inertia about point O. Summation moment about point O is equal to moment of inertia about point O alpha, or angular acceleration. And we're gonna assume the clockwise direction as positive. So what we have here, the summation of moment, we have the external moment mt in the clockwise direction and positive, and the spring or the torsion bar moment is on the counterclockwise direction. Jg, what happened? Jg divided by L and multiplied by the angular displacement. Is equal to the moment of inertia multiplied by the theta dot dot. So from here, again, our concept is to separate the terms of coordinate on the different side with the input. So we're gonna have I theta dot dot plus Jg divided by L theta equal to mt. I hope you're familiar with this kind of relationship. You may remember mx dot dot plus kx equal to ft for the linear system, that you have only one spring and mass and have force. You can derive equation of motion in the terms of mass, spring constant, and external force. In this case, for the rotational motion, the moment of inertia is the inertia property of the disk. I forget to put this for you, sorry. I is the moment inertia or inertia property of the disk multiplied by acceleration plus the stiffness property multiplied by the displacement equal to the input force or moment. This is the torsional stiffness. Okay. This will be the last example before we have a break, okay? We're gonna take maybe about 10 minutes for this example before we have break. So this is a pulley and a mass and spring system. Gray box on the screen.
Yeah, the gray box.
Check. I think we may better to have a break to solve the problem of the gray box. How do you think? Okay, we're gonna have a break first. for 10 minutes. And we're gonna continue from 3:36. Okay, 10-minute break.